Good day, grade 12 learners, and good day, colleagues. This is a continuation of the presentation that I did about the exam prep about a month ago. But I'll just recap on what I did then, and then we'll continue. If there's time, I'll also go back to what you did. But I sent you, the subject advisors and your teachers sent you the link of the first presentation. Remember, here we are trying to make sure that you get rid of any misconceptions and rectify any mistakes that maybe you made during September exam, or the mistakes that were made by last year's learners, so that you don't do the same mistakes. Now, in my last presentation, I talked about a reaction rate. Now, remember I said to you, you might be asked to draw a graph. It can either be a graph of one of the reactants or a graph of one of the products. Now, in this case, it is a graph of a product. For example, when magnesium reacts with hydrochloric acid, it forms magnesium chloride and hydrogen. So this is a graph of hydrogen. Now, this means that before magnesium and hydrochloric acid reacts, there would be nothing of hydrogen. And as magnesium and hydrochloric acid react, then more and more of hydrogen is formed. And then there will come a point where this graph has to be horizontal there at the top. Remember, this reaction is just a single reaction. It moves from reactants to products. So it means where there is a horizontal section, it shows that the reaction is complete. Why would the reaction be complete? It is because either both the reactants or one of the reactants is used up. So there is no longer two reactants to react to form the hydrogen that we're drawing now. And then, or you might be asked, for example, to draw a graph of the reactants. Now remember, products are being formed, so their graph will increase as it is shown there, because they are being formed. Nothing of the products were there at the beginning, and as they are being formed, their amount will increase. Now, reactants react, so as they are being used, their amount will decrease. Now, there might be one of the reactants that is a limiting reagent. In other words, there's only enough for it, enough amount for it to react. And then there might be another reactant where there is more than enough for it to react. So not all of it will react. Some of it will remain unreacted. So that reactant that remains unreacted after one of them has been completely used, that one that remains unreacted, we call it a reagent in excess or a reactant in excess. It means not all of it will react. But you can see we started somewhere at the top, and then it reacts, it gets used. After some time, we are going to have a horizontal line there showing that the reaction is complete. Why is the reaction complete? Because the second reactant has been used up. How do you see that it has been used up? You can see it has reached the x-axis, means there's no mass anymore left. It means nothing of that reactant is left. Now, in chemistry, there are a number of stoichiometric calculations that we do. We do stoichiometric calculations in reaction rate, in equilibrium, in acids and bases, and so on. Now, the stoichiometric calculations, what is important for you to know is you will use the equations that have the number of moles. So it is important to you to determine which of the reactant will be used up, because when you know how much of it has been used up, then you can use that particular reactant to get maybe the second reactant, how much will be used on that second reactant, or you will be able to get how much of the product was formed. But you do not use the one that is in excess, because in the one that is in excess, you don't know how much of it will react. So you use the one that reacts completely, because you know that if you are given 2 grams, if you are told that it reacts completely, then you know 2 grams of it has reacted. Then you can use that 2 grams of that reactant to get the other masses of the other reactants. Fine. Now, for example, I did this example earlier. I said magnesium earlier this year. I said magnesium reacts with hydrochloric acid to form magnesium chloride and hydrogen. Now the question is, initially they add 250 cubic centimeters of hydrochloric acid that has a concentration of 0.5 moles per cubic decimeters to 1.2 grams of magnesium in the test tube. So it reacts, it is a reaction of magnesium and hydrochloric acid. Now they are telling you that the mass of magnesium that is used is recorded at regular time intervals. Now you can see that in the graph, you started with a mass of 1.2 grams as was told in the statement, and the graph goes completely to the x-axis, which is 0. It means all of the magnesium reacts. It means magnesium is our limiting reagent. Now that would mean hydrochloric acid will be in excess. Now they continue telling you that calculate the number of moles of unreacted hydrochloric acid in the test tube. Obviously, if there's something that remains unreacted of hydrochloric acid, it means hydrochloric acid is in excess. Now, because you know all of the 1.2 grams of magnesium reacts, then you use that one of magnesium to get the others. Now, always check a formula that has the number of moles, or that you can calculate the number of moles of what was given. And then you use a balanced equation to calculate the number of moles of the one now that you want to calculate. Now, in this case, you can see you are given the mass of magnesium. So you go and check the formula that has mass, where you can calculate the number of moles. So that formula is N is equal to mass over molar mass. So the number of moles of magnesium will be the mass of magnesium divided by the molar mass of magnesium. Therefore, the mass of magnesium that completely reacts is 1.2 grams, and the molar mass of magnesium we can get from the periodic table, it is 24 grams per mole. Therefore, the moles of magnesium that reacted with hydrochloric acid is 0.05 moles. Now you want to calculate, to check the 0.05 moles of magnesium will react with how many moles of hydrochloric acid. Use your balanced equation. Now you can see that in your balanced equation, if you have 1 mole of magnesium, then 2 moles of hydrochloric acid react. What does that mean? It means the moles of hydrochloric acid that react is twice the one of magnesium. Therefore, you say number of moles of hydrochloric acid is twice the number of moles of magnesium that react. Therefore, now that you have calculated the moles of magnesium, it means it is 2 times 0.05. Therefore, the moles of hydrochloric acid that has reacted with magnesium will be 0.1 moles. Now, the question was calculate the number of moles that has not reacted. So the one that has reacted of hydrochloric acid is 0.1. But how many moles did you start with? You know that you were given the volume of hydrochloric acid and the concentration of hydrochloric acid. So which formula can you use that can enable you to calculate the moles of hydrochloric acid that you started with? The one that has the volume and the concentration, it will be the one of C is equal to N over V. So to calculate the number of moles of hydrochloric acid, you take the concentration of hydrochloric acid, which is 0.5, multiplied by, remember the volume must be in cubic decimeters. Therefore, it will be 250 times 10 to the power negative 3, or 250 divided by 1000, which is 0.25 cubic decimeters. Therefore, the moles that we started with of hydrochloric acid is 0.125. Then it means the moles that of hydrochloric acid that have reacted, that remain unreacted, will be 0.125, the one that we started with, minus 0.1 that reacted. Therefore, the one that did not react will be 0.025 moles. So the most important thing is, when you do stoichiometric calculations, check the formula that will enable you to calculate the number of moles, and check which one is a limiting reagent. Then you can use that one to calculate the others. Fine. Now let us now continue on chemical equilibrium. Now, under chemical equilibrium, what is expected of you to know is what is an open and a closed system. An open system is the one that continuously interacts with the environment, like the one that we did now, where magnesium reacts with hydrochloric acid. It is an open system. In other words, nothing is sealed within a certain isolated system. Now, a closed system is an isolated system. In other words, it is isolated from its surroundings. It does not interact with the surroundings. And then you are expected to know how to define a reversible reaction, which is a reaction where products can be converted to reactants, or just give us an indication that you know that you'll start with reactants and they react to form the products, but those products will again react to go back to the reactants. When you explain something like that, we would know that you are talking about a reversible reaction. You must know that chemical equilibrium, it is that dynamic equilibrium where the rate of forward reaction equals reverse reaction. Or you know that at equilibrium, the concentration of reactants and the concentration of products remain constant. They are not equal, but they remain constant. But the ones that are equal are their rates, the rate of the forward and the reverse reaction. And then you must be able to list the factors that influence equilibrium, which is the concentration, the pressure, and the temperature. Now, let us check now equilibrium. What happens there? Say, for instance, you have a reaction, you are given a reaction, hydrogen plus iodine, it forms hydrogen iodide. So this means at the beginning, you will have hydrogen and iodine. Before hydrogen and iodine react, it means you will have nothing of hydrogen iodide. So when hydrogen reacts with iodine to form hydrogen iodide, we say that is a forward reaction. You can see it moves from left to right. So that is called the forward reaction. So when now hydrogen and iodine react, more of the hydrogen and iodine will be used. It means the amount of hydrogen and iodine will decrease. As the hydrogen and iodine react, they now form hydrogen iodide. Therefore, as the hydrogen and iodine react, more of the hydrogen iodide is formed. And then, as soon as the hydrogen iodide is formed, now it can now decompose back to hydrogen and iodine. So when hydrogen reacts with iodine to form hydrogen iodide, we say that is the forward reaction. It moves from left to right. As soon as we have hydrogen iodide, then it can decompose back to hydrogen and iodine. So hydrogen iodide can now form hydrogen and iodine. That is a reverse reaction. So a reaction that can move from reactant to product as well as from products to reactants, we say that that reaction is reversible. So you must be able to differentiate between a forward reaction, a reverse reaction, and a reversible reaction. So some of the candidates say a reverse reaction is a reversible reaction. No, a reversible reaction is that reaction that can be reversed. In other words, it can move forward as well as backwards. So it can move from reactants to products and again from products to reactants. So when we talk about the forward reaction, hydrogen and iodine will be the reactants of the forward reaction, and hydrogen iodide is the product for the forward reaction. But when we talk about the reverse reaction, remember now we are going back. It means now hydrogen iodide will be a reactant for the reverse reaction, and hydrogen and iodine will be the products for the reverse reaction. And the whole reaction with double arrows is called a reversible reaction. Now what happens now when you're supposed to calculate, to draw a rate versus time reaction, graph? Since you know that before hydrogen and iodine react, you'll have nothing of hydrogen iodide. And you know that as hydrogen and iodine react, they are decreasing. It means their concentration is decreasing. And you know from the factors that a decrease in concentration will result in the decrease in reaction rate. So as hydrogen and iodine are there, at the beginning, you'll have a high concentration of hydrogen and iodine before they react. It means as they start reacting, their rate of reaction will be high. But as they start reacting, they now get used up. it means their concentration decreases. As the concentration decreases of hydrogen and iodine, therefore the rate of the reaction will decrease. Meaning, remember, hydrogen and iodine are reactants for the forward reaction. It means the rate of the forward reaction will start decreasing. And then what do you know about the reverse reaction? You know that before hydrogen and iodine react, you had nothing of hydrogen iodide. Since there was nothing of hydrogen iodide, it means there was no rate of reaction. But as hydrogen iodide is being formed, it means its concentration increases. Then as the concentration of hydrogen iodide increases, it means the rate of the reverse reaction increases. Then this happens, the rate of the forward reaction decreases and the rate of the reverse reaction increases until such time that the rate of the forward reaction now equals the rate of the reverse reaction, and that point we call equilibrium. Fine. Now you can also explain that in terms of concentration or the amount. You know that you started with a certain amount of reactants or a certain concentration of reactants. But as these reactants react, their concentration decreases. And you know that you started with nothing of the products. But as more products are formed, their concentration increases. Then at some point, the concentration of the reactants will now remain constant, and the concentration of the product remain constant. You can see that it is now a horizontal line. So it means the concentration now does not change. At that point where the concentration of the reactants and the concentration of the products remain constant, we say that is equilibrium, chemical equilibrium. Note that we are not saying their concentrations are equal, but we are saying their concentrations are constant. Fine. Now, after equilibrium is reached, now it is there that we start talking about Le Chatelier's principle. According to Le Chatelier, when equilibrium in a closed system is disturbed by changing concentration, temperature, or pressure, the system will find a new equilibrium by favoring the reaction that opposes the disturbance. Now, the system will change in such a way to reduce the effect of change. So remember, we are now at equilibrium, where the concentrations of the reactants and products remain constant. Now what you now do, you either change the concentration of the reactants or the products, or you either change the temperature or the pressure. So a change in any of these three factors will disturb the equilibrium. Now the system does what? The system wants to go back to equilibrium. So what does it do? It opposes whatever that you did. In other words, if you have increased the concentration, the system wants to decrease that concentration so that you go back to equilibrium. Because we are already at equilibrium. If you change the temperature, for example, you decrease the temperature, the system wants to do what? To increase the temperature so that we go back to equilibrium. The same thing applies to pressure. So Le Chatelier's principle just explains that when we are at equilibrium and you change any of those three factors, the system will oppose that change that you do by doing what? By opposing or favoring something that will try to cancel what you did, so that we go back to equilibrium. This is known as Le Chatelier's principle. Now, what you will be expected to do, remember, this we have already done. Now we are at equilibrium. So whatever that you change after equilibrium, it is where now we will be talking about Le Chatelier's principle. And you'll be expected to draw the graph of concentration versus time, as well as the graph of rate of reaction versus time. That will, whatever that will occur or will happen according to whatever that you have changed. So you draw the graph to show what will happen to the concentration and what will happen to the rate of the reaction by the factor, due to the factor that you have changed, that has disturbed equilibrium. Now let us do examples of what I was just talking about. Say for instance you have a reaction where N2O4 reacts to form NO2. Now remember, N2O4 is a reactant for the forward reaction and NO2 is a product for the forward reaction. Now as soon as NO2 is formed, then it can go back to N2O4. Therefore, NO2 is the reactant for the reverse reaction, NO2 is a reactant for the reverse reaction, and N2O4 is a product for the reverse reaction. Now, this means this reaction is reversible. Now, the reaction occurs and is allowed to reach equilibrium. And then at equilibrium, now what do? You increase the concentration of NO2. Remember, we said when you change either concentration, temperature, or pressure, what happens? The equilibrium is disturbed. Now, what does the system want to do? Since you have increased the concentration, the system wants to oppose what you did. It means the system will want to decrease that concentration of NO2. How will it decrease the concentration of NO2? By favoring the reaction that will use that added NO2. And which reaction uses NO2? It is the reverse reaction. It means due to the fact that you have increased NO2, therefore the reverse reaction will be favored, so that the NO2 that you added will be used, so that the concentration of NO2 can decrease until we reached a second equilibrium. Now, you might be asked to draw the graph showing what will happen after equilibrium is disturbed. So at equilibrium, remember, the concentration of everything remains constant. So all your substances, you'll draw their concentration as constant. So in this case, our substances are only N2O4 and NO2. So they are the substances, and the graph is constant, showing that we are at equilibrium. Their concentrations remain constant. Now, the question was, the concentration of NO2 is increased. Which graph of NO2 is this one? It is the pink one. So you'll show that the concentration of NO2 is increased by showing the line that moves upward, showing the increase. Now, what happens now according to Chatelier? It means the reaction that will use the added NO2 or the added concentration of NO2 will be favored. Which reaction is that? It is the reverse reaction. If we favor the reverse reaction, what will happen to the concentration of NO2? The concentration of NO2 will decrease. And if we favor that reverse reaction, what will happen to concentration of N2O4? Since NO2O4 will be formed, it means its concentration will increase. And this happens until we reach a new equilibrium. How will we see that new equilibrium is reached? It will have another horizontal lines showing that the concentrations have remained constant. Now, what is important for you to note is when you draw those graphs, bear in mind that the reaction is balanced. So when you check, in this case, the number of moles of NO2 as twice the number of moles of N2O4, meaning the change of NO2 that will happen will be twice the change of N2O4 that will happen. So this decrease in NO2 will be twice as much as an increase in N2O4 because of the number of moles of the two. Now, you might also be expected to draw the graph of the rate of reaction versus time. Now, in this case, what you do there, you say, okay, now we are at equilibrium. So where the rate of the reverse reaction equals the rate of the forward reaction. Now at equilibrium, the concentration of NO2 was increased. What do you know about the relationship between concentration and rate? You know that when concentration is increased, the rate of the reaction will increase. But NO2, you know that it is the reactant for the reverse reaction. It means an increase in concentration of NO2 will increase the rate of the reverse reaction because NO2 is the reactant for the reverse reaction. So the rate of the reverse reaction will increase. And then when the rate of the reverse reaction increases, what happens to NO2? The concentration of NO2 will now decrease because NO2 is being used. When the concentration of NO2 decreases, what happens to the rate of the reverse reaction? The rate of the reverse reaction will start decreasing. And as the rate of the reverse reaction increases, what happens to N2O4? Then N2O4 now increases, remember. Therefore, as the concentration of NO2O4 increases, the rate of the forward reaction will now increase. Therefore, the rate of the forward reaction will increase, and the rate of the reverse reaction will decrease until a new equilibrium is formed. Remember, you increase the concentration of NO2. Therefore, you increase the rate of the reverse reaction, because NO2 is a reactant for the reverse reaction. So as you increase the rate of the reverse reaction increases, then NO2 is used and N2O4 is formed. Therefore, NO2 as it is used, its concentration decreases, and N2O4 as it is formed, its concentration increases. So NO2 is a reactant for the reverse reaction. It means the rate of the reverse reaction will decrease. N2O4 is a reactant for the forward reaction. It means the rate of the forward reaction will increase until new equilibrium is reached. So do the graphs of the opposite, either when NO2 is decreased, or NO2 and N2O4 are decreased. So when NO2 is decreased or NO2 is increased, as well as when N2O4 is increased and decreased. Do all those graphs. Now the second factor that affects equilibrium is temperature. I just wanted us to quickly recap on the grade 11 material about temperature, about the exothermic and endothermic reaction, about the graphs of potential energy versus the reaction pathways that will show what happens between the exothermic and endothermic reaction. Remember, in grade 10, you did a graph showing that for reactants to react, energy, a certain amount of energy must be absorbed by those reactions so that those bonds of the reactants can be broken. And then for the products to be formed, a certain amount of energy must be released or must be liberated so that the products can be formed. So this is the combination of your grade 10 and grade 11 work, where now, because there's that minimum amount of energy that must be absorbed for a reaction to occur, for those bonds of reactants to be broken, therefore you must remember that the definition of that amount, minimum energy needed for the reaction to take place, is an activation energy. So that is an activation energy. You must know how to define activation energy. It is the minimum energy needed for the reaction to take place. So there must be a certain minimum energy that must be absorbed for the reactants to react. In other words, for the bonds of the reactants to be broken, and there must be a certain amount of energy that must be released for the bonds of the products to be formed. But in between the reactants reacting and the products forming, we have a state that is called the activated complex. In other words, the reactants have started reacting, the bonds have started to be broken, but new bonds have not started to be formed. So it is that intermediate state between reactants and products. We call that an activated complex. Now, in an exothermic reaction, a small amount of energy needs to be absorbed, but a large amount of energy must be liberated in an exothermic reaction. So a small amount of energy must be absorbed for the bonds to be broken, but a large amount of energy must be released for the bonds, new bonds to be formed. So since more energy is liberated than the one that is absorbed, therefore the energy of the products will be lower than the energy of the reactants. That is in an exothermic reaction. Now, as a result, when we summarize this, we just say it is that reaction where energy is released. Why do we say that? Because more energy is released than the one that is absorbed. So when we summarize that, we just say it is a reaction where energy is liberated. But actually, it is incorrect to say that. You need to say more energy is released than the one that is absorbed. Because you must know that for any reaction to occur, there is a certain minimum amount of energy that must be absorbed. Now, in this case, since you can see, remember when you calculate the delta H, it is the energy of the products minus the energy of the reactants. So the energy of the products is lower than the energy of the reactants. Therefore, it means delta H will be negative, or we say it is less than 0. That is an exothermic reaction. Now, in an endothermic reaction, the energy that is absorbed is larger than or is more than the energy that is liberated. The energy that is absorbed for the reaction to occur, or the energy that is absorbed for the reactants, the bonds of the reactants to be broken, is larger than the energy that is liberated for the products or the bonds of the products to start forming. So because the energy absorbed is larger than the energy liberated, in a nutshell, we just say an endothermic reaction is that reaction where energy is absorbed. And then when you have a look, because more energy is absorbed than the one that is released, it means energy of the products will be more than the energy of the reactants. And then energy of the products minus energy of the reactant will give you a delta H that is positive, or the one that is greater than 0. Now, use this background when you explain the influence of temperature, whether it is with the graphs or it is with Le Chatelier's principle. Now, say for instance we have an equation that is given: N2O4 reacts to form NO2 and then can go back to N2O4. Now, delta H is greater than 0. Remember the one that is written there, it means it is for the forward reaction. It means the forward reaction is endothermic. That automatically means the reverse reaction is exothermic. Now, we are told that a reaction is allowed to reach equilibrium, and then at equilibrium the temperature is then increased. Now, when you increase the temperature, remember I said either you change the temperature, the concentration, or the pressure, you disturb equilibrium. So in this case, you have increased the temperature. It means you disturbed equilibrium. So what does the system want to do? It wants to go back to equilibrium. How will it go back to equilibrium? Remember the temperature was increased. Remember in grade 10, you related temperature to energy. You said that temperature is a measure of what? Of that particular energy. Meaning when the temperature increases, actually it means the energy also has increased. So it means in this case we have increased energy by increasing what? The temperature. So what does the system want to do now? The system wants to decrease that particular energy. How will it decrease the energy? It will favor that reaction that needs that energy, or that will absorb that energy. Which reaction is that? It is the endothermic reaction. It means by an increase in temperature, the forward reaction will be favored. Why is the forward reaction favored? Because the forward reaction is the endothermic reaction. So if the forward reaction is favored, what happens to the amount of NO2? It means the amount of NO2 will increase and the amount of N2O4 will decrease. That means the concentration of NO2 will increase and the concentration of N2O4 will decrease. Therefore, you will draw that when you increase the temperature, you have favored the endothermic reaction, which is the forward reaction. So by favoring the forward reaction, the concentration of NO2 increases and the concentration of N2O4 decreases, and then a new equilibrium is formed. Remember, equilibrium, the concentrations will now start to remain constant, must remain constant. Don't forget the number of moles. So since the moles of NO2 is twice the moles of N2O4, it means the change in the amount of NO2 the concentration of NO2 will be twice the change in the concentration of N2O4. Fine. Now, you might also be expected to draw the rate versus time graph. Remember, we are at equilibrium. where the rate of the forward reaction equals the rate of the reaction, a reverse reaction. And then you were told that the temperature is increased. Remember, when you talk about this reaction occurs in the same container. So there is endothermic reaction and exothermic reaction in the same container. So when you increase the temperature, you increase the temperature of the whole system, meaning the temperature for the forward reaction and for the reverse reaction, it means it increases. So now, excuse me, you are asked to draw the graph of rate of reaction. What do you know about the relationship between temperature and the rate of the reaction? You know that when you increase the temperature, the rate of the reaction increases. The rate of which reaction? Since both reactions occur, it means the rate of both reactions will increase. So you'll draw the horizontal lines that show that the rate of both the forward and the reverse reaction increase. But now, what else do you know? You know that an endothermic reactions wants the temperature to be increased so that the energy can be increased, so that it can absorb the energy. So since the forward reaction was the one that was favored, it means the rate of the forward reaction will increase more than the rate of the reverse reaction. In other words, what I'm saying to you is always when you increase temperature, the rate of an endothermic reaction will increase more than the rate of the exothermic reaction. Why? Because the endothermic reaction wants to absorb that added energy. Now, when an endothermic reaction is favored, it means the concentration of NO2 will now increase and the concentration of N2O4 will decrease. Remember, N2O4 is the reactant for the forward reaction. If its concentration decreases, what will happen to the rate? It means the rate of the forward reaction will now decrease, and NO2 is the reactant for the reverse reaction. So if its concentration increases, what happens to the rate of the reverse reaction? It increases until a new equilibrium is established. So go and do the graphs also of the temperature decrease. Remember, when the temperature decreases, the rate will decrease. It means the horizontal line will move downwards for the rate graph. Now let us do the next one. The next one is N2O4, the influence of pressure. Say for instance we have N2O4 forming NO2 and equilibrium is established. And then at equilibrium, pressure is increased by decreasing the volume. Now remember, nobody said any of the reactants were removed or any of the reactants were added. It means the number of moles of the substances, both the reactants and the products, the number of moles remain constant. So if number of moles is constant, then you must know that concentration is inversely proportional to the volume. Now we are told that the volume is decreased. So that means if the volume is decreased, the concentration will increase. The concentration of what? Remember, the volume is for the container. So if the volume is for the container, it means the concentrations of everything inside the container will increase. So in the container we have NO2, we also have N2O4. So when you're supposed to draw the graph now of the concentrations, remember we're at equilibrium, and then what happened? We increased the pressure by decreasing the volume. So when you decrease the volume, because the number of moles is constant, it means the concentration will increase. So you now draw the line horizontal upward to showing that the concentration of both the substances increases. And then you go back now to Le Chatelier. You say, you know that an increase in pressure will favor the reaction leading to least number of moles of gases, or it favors the reaction that results in less number of moles of gases. The word of gases is important. Now, when you have a look at your reaction, you can see on the left hand side you have 1 mole, on the right hand side you have 2 moles. So from left to right you move from 1 to 2. That is an increase in mole. But from right to left, you'll move from 2 to 1. That is the decrease in mole. It means by increasing the pressure, you favor the reaction that results in least number of moles of gas, meaning the reverse reaction will be favored. So if the reverse reaction is favored, what happens to the concentration of NO2? The concentration of NO2 will decrease and the concentration of N2O4 will increase until we reach a new equilibrium. Don't forget, the change in those concentration depends on the number of moles. So the change of NO2 concentration will be twice the change of N2O4, since the number of moles of NO2 is twice the number of moles of N2O4. Now, when we're expected to draw the rate versus time graph, we are at equilibrium where the rate of the forward reaction equals the rate of the reverse reaction. Now, what happened? You increase the pressure by decreasing the volume. Remember, when you increase the pressure by decreasing the volume, what happened to the concentration? The concentration of both the substances increased. So what do you know about the relationship between rate and concentration? You know that when the concentration increases, the rate of the reaction increases, meaning the rate of both the reactions will increase. Now, you go back to Chatelier, you say, an increase in pressure favors the reaction that leads to least number of moles of gas, which is the reverse reaction. It means the rate of the reverse reaction increases more. And then, so you show that on the graph. And then, when the reverse reaction is favored, what happens to the concentration of NO2? It decreases and the concentration of N2O4 increases. Therefore, the rate of the forward reaction will increase and the rate of the reverse reaction will decrease until new equilibrium is established. Also do the graph when the pressure is decreased. Now let us summarize what I've just talked about. When you increase the concentration of the reactants, remember, according to Le Chatelier, the system will now want to decrease that concentration. Remember, the reactants are on the left-hand side. So when you increase the concentration of the reactants, the system wants to decrease that concentration of the reactants. How will it decrease that concentration of the reactants? By using those reactants. Therefore, the forward reaction will be favored. When we increase the concentration of the products, therefore, the reverse reaction will be favored because the system wants to use that added concentration of the products. Therefore, the reverse reaction will be favored. But what happens when you decrease the concentration of the reactants? Since the concentration of the reactants was decreased, the system wants to do what? To increase the concentration of the reactants, meaning it wants to form more reactants. Therefore, it means the reverse reaction will be favored. When you decrease the concentration of the products, the system wants to form more products. Therefore, the forward reaction will be favored. When the temperature is raised, an endothermic reaction is favored. When the temperature is lowered, an exothermic reaction is favored. And then the pressure, when the pressure is raised, the reaction which produces least moles of gas will be favored. And when the pressure is lowered, the reaction which produces the most molecules of gas is favored. You use this Le Chatelier's principle when explaining what will happen. You also use it when you draw the graphs of concentration versus time, as well as the graphs of rate versus time. Now let us talk about equilibrium constant values. You know that when you are calculating the equilibrium constant, you will use the concentrations. So it will be the concentration of whatever that is on the right hand side, which we usually call the product, divided by the concentration of everything that is on the left hand side, which we usually call the reactants. So now, if the Kc is greater than 1, or if the Kc value is high, it means there is more, the concentration of the products is more than the concentration of the reactants, or the concentration of the products is higher than the concentration of the reactants. That is why the Kc is greater than 1. So it means that reaction that has resulted in Kc that is greater than 1, its equilibrium position lies far to the right because there's more concentration of products than the one of reactants. Now, when the Kc value is less than 1, or when we have a low Kc value, it means the concentration of the substances on the left-hand side, which we call the reactants, is greater than the concentration of the substances on the right-hand side, which we call the product. It means this reaction actually does not favor the formation of the product. It means the equilibrium position lies far to the left because the concentration of the substances on the left-hand side is higher than the ones on the right-hand side. Now, let us carry on. What is the significance of the actual Kc value? Excuse me. Remember, the only factor that will affect the Kc value, or that can change the Kc value, is the temperature. When you change the concentration, the Kc value will remain constant. When you change the pressure, the Kc value will remain constant. The Kc value can only change when temperature is changed. Whether it's increased or decreased, you will check. And you'll also check which of the sides will be favored. But the Kc value can only be changed by a change in temperature. So to increase the Kc value, you know that it means you want to increase the concentration of the products. It means you will do to the temperature whatever that will make sure that the forward reaction is favored, so that the concentration of the products can increase, and then the Kc value will be able to increase. If you want to decrease the Kc value, it means you will change the temperature in such that you want to favor the reverse reaction, so that the products of the concentration of the reactants can be greater than the concentration of the products. Now, Kc expressions. Remember, when we write our Kc expression, we use the concentration of the substances on the right hand side, which we call products, divided by the concentration of the substances on the left, which we call the reactants. But when we're supposed to do the calculations based on the Kc, in other words, Kc calculations, saying Kc is the concentration of the products divided by concentration of reactants carries no mark. You must show us what are those products. For example, here in 1.1 we have H2O2 forming H2O and O2, and make sure that the equation is balanced. And then you must also remember that pure liquids and solids, their concentrations remain constant. Since their concentrations remain constant, when you write your Kc value, you exclude pure liquids and solids. So you only include the aqueous solutions and gases. So Kc will be concentration of the substances on the right hand side. Remember, H2O is a pure liquid, so you want to include it. It will be concentration of O2 divided by the concentration of H2O2 raised to the power of the moles that were balanced with. 1.2, the Kc will be concentration of CaCl2 multiplied by the concentration of CO2. Remember, H2O is a pure liquid, so you won't include it. Divide by the concentration of HCl raised to the power 2. Calcium carbonate is a solid, so its concentration is constant. You don't include it. The same thing applies to 1.3. Now, when doing Kc calculations, it is important for you to understand when we're talking about the reactants and when we're talking about products, what happens. Remember, when the reactants react, they get used. It means their amount decreases. But products, because they are formed, you start at the beginning, before the reactants react, you start with nothing of the products. So the product will be 0, but as the reactants react, more of the products will increase. So that is why when we do the Kc calculations, it is important to know which one are the reactants and which ones are the products. So I personally prefer to include the arrows to show on the left hand side I'm dealing with reactants, on the right hand side I'm dealing with products, so that I can remember which ones will decrease, which ones will increase. But that's just my personal preparation. So if you include that arrow there, nobody will penalize you, but at least you will already see which one is the reactant and which one is the product. Now you are told that you have 0.396 moles of carbon monoxide at the beginning and 0.1648 moles of oxygen at the beginning. And you know that before the carbon monoxide and oxygen react, you'll have nothing of carbon dioxide. So initially you have what was given and nothing of carbon dioxide. And then you are told that at 0.0148 moles of oxygen reacted with CO. So the change is the amount that reacted for the reactants or the amount of product that was formed for the product. So you know that 0.0148 reacted of oxygen. Therefore, you know that reactants are being used, so you minus. Therefore, the at equilibrium, the one that will be left after the reaction of oxygen, it will be 0.15 moles. Now to get the moles of the other two, you will use the balanced equation. You can see that 1 mole of oxygen reacts with 2 moles of carbon monoxide, meaning moles of carbon monoxide is twice the moles of oxygen. Therefore, since you had 0.0148 moles of oxygen, twice of it will be the one of carbon monoxide, and also twice of it will be the one of carbon dioxide. Therefore, you get those moles. Then you remember carbon monoxide is a reactant, you minus, and then carbon dioxide is the product, it will give you the same number. Then to calculate the equilibrium concentration, you will just use the formula C is equal to N over V. Therefore, you divide the number of moles that you had at equilibrium by the volume that is given, which is 2 cubic decimeters. Therefore, you will get the concentration. Therefore, Kc expression, you write your Kc expression, you substitute the substances that you have calculated, the concentrations that you have calculated, and you'll get your answer. Now, you might be given another question where you have the reactants, but you were not given the one that reacted, but you were given how much was left at the end for carbon monoxide. So since you know that, for example, when you have money, when you have 5 rands and you are left with 3 rands, it means you have used 2 rands. So there you still minus. So it will be the ones that you started with minus the equilibrium moles to get the ones of that was used. And then you go back to the balanced equation. You can see carbon monoxide has the same moles as carbon dioxide. Already, if you have 0.0296 here, it means for carbon dioxide you will also have 0.0296. And you can see that 2 moles of carbon monoxide, 1 moles of oxygen. It means moles of oxygen is half the moles of carbon monoxide. Therefore, you can get those moles. Therefore, for the reactants, you minus, for the products, you add. And then you calculate the concentration and the Kc expression. I want to concentrate on this one. In this one, you were only given the moles of carbon monoxide and carbon dioxide at equilibrium. You were given nothing that you started with, you were given nothing that reacted or nothing that was formed. But you were told that at equilibrium, you have 0.3 moles of carbon monoxide and 0.15 moles of oxygen. And then you are given the Kc expression, the Kc value, which is 0.13. Remember, equilibrium must be at the same temperature as the beginning of the reaction. No temperature must be changed. Because when you change the temperature, remember, the Kc value changes. Now, since we are given the Kc expression, it means, remember, Kc is the concentration of carbon dioxide raised to the power 2 divided by concentration of carbon monoxide to the power 2 multiplied by concentration of O2. So for me to calculate the Kc expression, I need the concentration. But I'm already given the Kc expression. But I can use the concentration to get the concentration of what I don't know. It means from what I have, I can calculate the concentration of carbon monoxide and the concentration of carbon dioxide. So I already have the concentration of carbon monoxide and the concentration of carbon dioxide. I have the Kc value. It means I can calculate the concentration of carbon dioxide, which is 0.0148. Then you go back, okay, since I now have the concentration of carbon dioxide, go back and substitute it there in your table and move now backwards. The question was, calculate the initial mass of oxygen in grams. So you have first to calculate the moles of oxygen initially, then you'll calculate the mass. So you are now working backwards. Since you have the concentration, which formula can you use to calculate the number of moles? You know that it is N is equal to CV. So you can calculate the number of moles of carbon dioxide there, which will be number of moles of, concentration multiplied by the volume, which is 2 cubic decimeters. And then what else do you know? You know that for the products, I started with nothing. So if I started with nothing and ended up with 0.0296, it means I formed 0.0296. So when you have any of the changes, whether it is the reactants or the products, you know that you can use the balance equation to get the rest. Now, since I only need for oxygen, I check, okay, number of moles of oxygen is half the number of moles of carbon dioxide. Therefore, it means these moles will be half of 0.0296, which is 0.0148. Now I have what I started with, I have what was formed, what was used, how much did I start with? You know that if you started with 5 runs, you use 2 runs, you'll be left with 3 runs. Now you don't know how much you started with, but you know that at the end I have 3 runs and I know I've used 2 runs. It means how much did I start with? Therefore, you'll add the 2 to get the initial moles. Now that you have the initial moles, what was the question? Calculate the mass, initial mass of oxygen. So you go back to the formula, N is equal to mass over molar mass. You have the moles, which is 0.1648, and then you know that the molar mass of oxygen will be 16, but we have 2 oxygens, therefore it will be 32. You'll get the mass. So this is what I'm talking about. I said to you, every time when you have stoichiometric calculations, you'll use the formulae that have number of moles. Now, I want us to talk about negative marking. The reason why I wanted to talk about negative marking, last year in 2019, in question 6.3.2, we had a question here where the learners were given a balanced equation and were told that the reaction has reached equilibrium. And then the pressure is increased by reducing the volume of the container at constant temperature. How will this change affect the amount of carbon monoxide at equilibrium? So they have to tell us when the pressure is increased, how will that affect the amount of carbon monoxide at equilibrium? And then they must choose whether the amount of carbon monoxide will increase, decrease, or remain the same. And then they must use Le Chatelier's principle to explain the answer. What now happened here is learners know that when you increase the pressure, you will favor the reaction that will lead to smaller amount of moles of gas. Most of the learners said that when pressure is increased, the reaction that leads to smaller amount of gas molecules is favored, which is 1 mark. And therefore, they went back to the balanced equation and said, okay, on the right hand side I have 2 gas molecules, on the left hand side I have 1 gas molecule. So the decrease in gas molecules is the reverse reaction, and they quickly said the reverse reaction is favored. But most learners failed now to say if the reverse reaction is favored, it means the amount of CO will decrease, which is the first question. Why will this change affect the amount of CO? So what negative marking means? It means for the 2 marks of your answer, you must first, the 2 marks of the reason, you must first answer the question. If the answer is incorrect or if there is no answer, therefore you will lose the marks of the reason. So before you move to the next question, just check that you have answered all your questions, because these learners used the Le Chatelier's principle correctly and could have gotten the 2 marks of Le Chatelier's principle provided they had answered the question first, saying decreases. You can start with the reasoning and then at the end answer the question. It doesn't matter. What the marker will do, check whether the answer is there, give the mark for the answer, whether it's at the top or the bottom, it doesn't matter. Give the mark for the answer and then go to the reasoning or the application of Le Chatelier. So if the answer is not there, then it means it's 0 out of 3. So always ensure that you answer your question first before you give the reason. Now, let us now go to the next topic, which is electrochemistry. Now, I want us to talk about electrochemistry. Talk about electrochemistry, talking about both galvanic and electrolytic cells. Now, what you need to know there is the energy changes. You must know the energy changes in a galvanic cell. You must know the energy change in an electrolytic cell. You must know what an anode is. You must know what a cathode is. You must know the polarity of your electrodes in a galvanic cell and the polarity of the electrodes in an electrolytic cell. But what is important is that whether it's a galvanic or an electrolytic cell, anode is that electrode where oxidation occurs. The cathode is that electrode where a reduction occurs, whether it's electrolytic or a galvanic cell. At the anode, oxidation occurs. At the cathode, reduction occurs. But the polarity, in other words, for example, in a galvanic cell, you can see that the anode is negative. But in an electrolytic cell, it will be the other way around. The anode will be positive. So you cannot say now, for example, when we are asked to define an anode, say an anode is that electrode, it's a negatively charged electrode. You cannot, because it is negative in a galvanic cell, but it is positive in an electrolytic cell. So when you define an anode, you will say it is that electrode where oxidation takes place, because whether it is in an electrolytic cell or galvanic cell, at the anode, oxidation takes place. Now, in a galvanic cell, for the reaction or for the cell to be functional, the reactants must first react, or the chemicals must first react, and as the chemicals react, therefore you'll now have a reading on the voltmeter. So it means, the chemical reaction leads to electrical energy. So before the chemicals react, you will not have electrical energy. Meaning, a galvanic cell, it is that cell where the chemical energy will be converted to electrical energy. So there must first be a reaction of chemicals, then there will be a reading on the voltmeter. So chemical energy is converted to electrical energy. The reading on the voltmeter shows that there is electricity. So that is why we say chemical energy is converted to electrical energy. Now let us continue about that one. We have realized in quite a number of years that most grade 12 candidates cannot give an explanation correctly in terms of comparing the strength of oxidizing agents versus the strength of reducing agents. Some candidates would say a certain substance or a certain element is a strong reducing agent, and then again say the same element is a strong reducing agent, or they would say that element is a strong oxidizing agent, and then come again and say that particular element is a strong reducing agent. An oxidizing agent cannot be a reducing agent. A reducing agent cannot be an oxidizing agent. These two are two different elements or two different substances. Let us have a look at the table. you can see that you have an arrow on the right hand side, you have an arrow on the left hand side. It doesn't matter whether you're using table 4A or table 4B, it gives the same answer because they are the same thing. It's just that the other one starts with the whatever that was at the top in table 4A will be at the bottom in table 4B, but the arrows will be the other way around, showing that whatever that is a strong oxidizing agent in table 4A will still be a strong oxidizing agent in table 4B. So they are the same actually. Now, when you have a look at the table, you can see that you have arrows on the right hand side, you have arrow on the left hand side. In this particular table that I've shown you, the arrow that moves up on the right hand side, it says increasing reducing ability. And the arrow that moves down on the left hand side says increasing oxidizing ability. What does that mean? It means, remember this arrow is on the right hand side. It means in these equations, every substance that is on the right hand side of the arrow is a reducing agent. And on those substances on the right hand side of the arrow, when you move up the table, because the arrow is moving up, when you move up the table, it means the reducing ability increases. What does that mean? Aluminium is up there on the right hand side, remember. Aluminium is up there and is followed by manganese. It means aluminium is a stronger reducing agent than manganese, because as you move up, according to this table on the right hand side, as you move up, the reducing ability increases. Or you can use the reduction potential. You can see as you move up, the reduction potential becomes more negative. Therefore, you can say the most negative reduction potential, the reducing agent, in other words, the substance on the right, when you have a look at the reduction potential, the most negative reduction potential, it means the one that has the most negative reduction potential, the substance on the right, will be a stronger reducing agent than the substance on the right whose reduction potential is less negative. And then when we move to the left hand side, you can see that the arrow points downwards, saying increasing oxidizing ability. Substances on the left hand side of the arrow, meaning they are oxidizing agent, excluding the electrons, of course. And then when you move down your table, it means your oxidizing ability increases. So the one towards the bottom is a stronger oxidizing agent than the one towards the top on the left hand side of your arrow. And then what you can also say, remember when you're moving down now, the reduction potentials becomes more positive. So the substances on the left hand side, that corresponds to the more positive reduction potential, will be stronger oxidizing agent than the one that are at the top, where the reduction potential is less positive. So it is important for you to use the arrow. So you can either use the arrow or you use the reduction potentials, or you can use both of them. It's fine. Now what this means, let us have a look at lead half reaction and the copper half reaction. When you have a look at the lead half reaction and the copper half reaction, you can see that on the right hand side you have lead, you have copper. Therefore, you have a look at the arrow. You say, oh, the arrow says reducing ability. It means lead and copper are reducing agents. Now the arrow points up. It means when you move up, the reducing ability increases. That means lead is a stronger reducing agent than copper. And then when you have a look on the left hand side, you have lead ion, you also have copper ion. And you can see on the arrow, it means, it says increasing oxidizing ability. It means lead ion and copper ions are oxidizing agents. Now when you move down the arrow, it says when you move down, the oxidizing ability increases. it means copper ion has a copper 2 ion has a stronger oxidizing ability than lead 2 ion, or copper 2 ion is a stronger oxidizing agent than lead 2 ion. So can you see that you cannot say lead is a stronger oxidizing agent, because lead is not an oxidizing agent. It is on the right. It is a reducing agent. The one that is an oxidizing agent is lead ion. Now, what does this mean if we say lead is a stronger reducing agent than copper? Remember, a reducing agent will undergo oxidation and an oxidizing agent will undergo reduction. So lead is a stronger reducing agent than copper. It means lead will undergo oxidation, not the copper, because lead is stronger than copper in terms of reducing ability. So lead is a stronger reducing agent than copper, therefore lead will be oxidized. On the other side, copper 2 ion, is a stronger oxidizing agent than lead 2 ion. Therefore, copper 2 ion will be reduced or will undergo reduction. So this is what I've been talking about. So it will be lead that is oxidized and it will be copper ions that are reduced. Now say for instance now we're talking about a galvanic cell. Here's a galvanic cell. We are talking about a lead and copper. So for this cell to be functional, you must have a lead half cell and a copper half cell. What is in the lead half cell? There must be a lead electrode as well as a solution that will form that has lead ions. For example, that solution that we call an electrolyte, that electrolyte must be soluble in water so that it can produce ions. Which ions? The lead ions and whatever negative ions. So in this case, we had lead nitrate. It means it will be lead ions and nitrate ions. And as this was lead nitrate, it means the number of positive ions equals exactly the number of negative ions in the beaker, because that was lead nitrate, and lead nitrate is an is soluble in water. So since it is soluble in water, it will form lead ions and nitrate ions. And then in the next half cell, we'll have a copper half cell. What constitutes a copper half cell? There must be a copper rod, which is an electrode, as well as a soluble copper salt. That copper salt, in this case, we have used copper sulfate. So that salt now will form copper ions and sulfate ions. You can see we have equal number of positive ions and negative ions. Now, remember we said it is a galvanic cell. So for the galvanic cell to be functional, we said chemical energy must be converted to electrical energy. So it means these chemicals must first react so that we can have a reading on the voltmeter. So let's see now what happens. We connect the lead electrode to the copper electrode, and then after connecting these two, nothing happens to the circuit. In other words, there is no reading on the voltmeter. It means chemical energy has not yet been converted to electrical energy. Why? Because we need a salt bridge. That is why when you are asked what a salt bridge does, what it does, you always say it completes a circuit. Now that there's a salt bridge, the circuit is complete. There will be movement of ions and movement of electrons. So since the circuit is now complete, there will be a reading on the voltmeter. Fine. Now I said to you, we have the same number of positive ions and negative ions in both the beakers. Remember, the concentration of your electrolytes must always be 1 mole per cubic decimeter, and the temperature, you know, it must always be 25 degrees Celsius. Now, let us carry on then. Now you go back to your table. You just shown in the table that lead is a stronger reducing agent than copper. If lead is a stronger reducing agent than copper, it means lead will be oxidized. It means this half cell of lead, that is where the oxidation will occur. And we just said the electrode where oxidation occurs is called the anode. Now what happens? That lead electrode undergoes oxidation. So it forms lead ions. Remember in here, you already had lead ions and nitrate ions. And the number of positive ions and negative ions were equal. But now, this lead electrode undergoes oxidation. It means now the positive ions will increase because more lead ions will now be formed. So in this case, on the left hand side, on the lead half cell, we now have more positive ions. And then on the other side, you can see that copper is a stronger oxidizing agent than copper ion is a stronger oxidizing agent than lead ion. It means copper ions will undergo reduction. Remember, you had the same number of positive ions as negative ions there. But now some of the copper ions now will absorb, gain electrons and be reduced. So it means some of the copper ions will now gain electrons and form copper. It means in this case the positive ions will decrease because they undergo reduction, some of them. Therefore it means we'll have more negative ions in the copper half cell than positive ions. In the lead half cell we have more positive ions than negative ions. Now what happens there? That is where the salt bridge comes in. Now, since on the left hand side we have more positive ions, therefore, what happens there? It means the salt bridge must allow the negative ions to migrate towards the lead electrode. The lead half cell. Why? So that it can maintain electrical neutrality. That's what you always say to us. You either say the function of a salt bridge is to complete the circuit, or you say it maintains electrical neutrality. Why? Remember, we had more positive ions here. So the salt bridge will allow the negative ions now in the salt bridge to migrate towards the lead electrode so that they can neutralize those positive ions so that we can go back to neutral solution. The same thing applies to the copper half cell. Remember, we had more negative ions in the copper half cell because the copper ions, some of the copper ions were underwent a reduction. So now the positive ions in the salt bridge will migrate towards the copper half cell so that they can neutralize the negative ions. And then in that case, now we have a complete circuit. So in the internal circuit there is movement of ions. You can see there's migration of ions. Remember, negative ions migrated towards the lead electrode, excuse me, positive ions migrated towards the copper electrode. And then in the external circuit we saw that lead undergoes oxidation. It means it loses electrons, and copper ions undergo reduction, they gain electrons. Therefore, electrons migrate in the external circuit from the anode to the cathode. So the anode is negatively charged. It means it has an excess of electrons. That's why it can donate electrons. And the cathode has a shortage of electrons. So that's why it is able to gain electrons and undergo reduction. And a reduction takes place there at the cathode. Fine. Now we can see that the reaction now can occur. It means at the end of this whole process, there will be a reading on the voltmeter. Fine. This chemical energy is spontaneously converted to electrical energy. That's why there will be a positive reading on the voltmeter. And when you do when you are expected to calculate the EMF of the cell, you will see that the reading that you'll get there, or the answer that you'll get there, will be a positive answer, showing that the reaction is spontaneous. Fine. Now, in this case, we have seen that lead underwent a oxidation and then copper ions a reduction. So you might be expected to write the cell notation. When you write the cell notation, in the middle, you must always have double lines showing that there was a salt breach. So the double lines represent the salt breach. And then the left-hand side, you'll write the oxidation, and then the right-hand side, you'll write reduction. So you know that lead was oxidized to lead ions. So it will be Pb to Pb2 plus. And in between these two, you'll write a line. That line is what we call the line of phase separation. You can see that lead is a solid because it was the rod, remember? And then lead ions is an aqueous solution. Remember, it was in the solution. So because they are different phases, you put that line. It's called the line of phase separation. And then on the right hand side, I said is the reduction. So it is copper ions reduced to copper. So it will start with copper 2 plus to Cu. Since these are in different phases, you'll put the line of phase separation. Say for instance, you have another reaction where, for example, you had a zinc forming zinc ions, but hydrogen ions undergoing a reduction to form hydrogen. Can you see that in this case, you have the zinc rod, which is a solid. Remember, in other words, for you to have a reading on the voltmeter, that voltmeter must be connected to the electrodes as you saw. But those electrodes must be solid so that you can connect those the voltmeter. And those electrodes must conduct electricity so that the circuit can be complete, so that again there will be electricity produced. So those electrodes must be able to conduct electricity. Now in this half cell, the other half cell, the hydrogen half cell, does not have a solid. You know, hydrogen does not conduct electricity and it's not a solid, it's a gas. In that case, you need an electrode where you will be able to connect the voltmeter, and that electrode must be a conductor of electricity. But that electrode must not be reactive, because if it is reactive, instead of hydrogen reacting, it means it will be that electrode reacting. So it must be an inert electrode. It is unreactive, and that example of that unreactive electrode, it is platinum. So why do we need this electrode here instead of a solid electrode? We know that the reaction is between hydrogen and zinc. Hydrogen is a gas. So how would you connect a voltmeter to a gas? So for us to be able to connect that voltmeter, we need a solid. But the reaction is not on that solid. It is on of hydrogen. It means that solid must be able to conduct electricity, but it must not react. So we said it is inert. So we usually use platinum. So in this case, that is why when we write our reaction, we don't include platinum. Platinum is just there to assist us to have a complete cell where we'll have a chemical energy being converted to electrical energy. Fine. Now in that one, you can see oxidation. Zinc was oxidized to zinc ions. So it will be zinc and zinc ions on the left hand side, and the line of phase separation and the salt bridge. And then we can see hydrogen ions were converted to hydrogen gas. Since hydrogen ions and hydrogen gas are in different phases, you'll include the line of phase separation. But this hydrogen, since it is not a solid, we used platinum for us to be able to connect to the voltmeter, so that and platinum is a conductor of electricity, so that we can have that voltmeter reading, so that chemical energy can be converted to electrical energy. So platinum did not take part in the reaction, but platinum was used as an electrode. So you include it here just to show that platinum is the electrode, because in a cell notation, on the extremes are your electrodes. So platinum was used as an electrode, but when you write your reaction, you don't include platinum because it is inert. It does not react, take part in this particular reaction. And then, as you have the voltmeter reading there at the top, as time goes on, the reading on the voltmeter decreases. Why does it decrease? It decreases because the concentration of the electrolyte, of the reactant, the concentration of the reactant ion decreases, and the concentration of the product ion increases. Therefore, the reading on the voltmeter will decrease. If the concentration of the reactant ion increases and the concentration of the product ion decreases, therefore the reading on the voltmeter will increase. Now, as that reading on the voltmeter decreases because the concentration of the reactant ions decreases, that reading on the voltmeter will decrease. It will decrease until such time the reading is 0. And when the reading on the voltmeter is 0, and that happens after some time, when the reading is 0, we say that that particular cell, that particular reaction has reached equilibrium. Remember, it is a reaction of chemicals producing electricity. So that particular reaction has reached equilibrium. And then it might happen, like last year it happened that they were told that, for example, the reaction is now continuing. And after a while, say for instance, you are talking about this half reaction of zinc and hydrogen. After a while, you add more zinc nitrate. So what do you know about zinc nitrate? It is soluble in water. So it can form zinc ions and nitrate ions. Therefore, the zinc ions that are formed will increase the concentration of the zinc ions of that are already in the solution. It means the concentration of your product ion will be higher, and the concentration of your reactant ions will be low. What does that mean? It means the reading on your voltmeter will decrease. And then you might be asked to explain using Le Chatelier's principle what will happen. You know that using Le Chatelier's principle, if you increase the concentration of zinc ions, therefore the reaction that will use those zinc ions must be favored. It means you'll favor the reverse reaction. No? Okay. Now, let us now continue. Another mistake that some of the learners make. Remember, when you're supposed to calculate the EMF of the cell, you are given the formula. For example, EMF of the cell equals E oxidizing agent minus E reducing agent. Instead of that, the learner will write E ox minus E red. If you write that one, you'll get no marks for the formula, because we don't know whether the ox is oxidation or whether the ox is oxidizing agent. So for you to get the marks, copy those formula as they are from the formula sheet. Fine. And then so let us also make sure that we don't use those unconventional abbreviations. Now let us talk about electrolytic cells quickly, and then we will be done. Excuse me. In an electrolytic cell, electrical energy must be converted to chemical energy. What does that mean? It means an electrolytic cell will not operate unless there is a source of electricity. So for example, there's a battery here, so that the electrical energy from the battery can cause the reaction of the chemicals. So without that energy, without that electrical source, there won't be a reaction of those chemicals. So for us to have electrical energy to chemical energy, we must have an electrical source, so that electrical energy can be converted to chemical energy. Those chemicals can react. Fine. So let us have an example where inert electrodes are used. What does inert electrodes mean? It means those electrodes do not take part in the reaction. So only the electrolyte reacts. So only the substance in the solution reacts. So in this case, we have decomposition of copper 2 chloride. So if we have copper 2 chloride, we know that we'll have copper ions and chloride ions. But because it is copper 2 chloride solution, since it is a solution, it is dissolved in water, there's also water that can take part. So it means we excuse me, we will have chloride ions and water as a reducing agents. We'll also have copper ions and water as oxidizing agents. So you'll have to use your table to check which of those reactions will occur. Will it be oxidation of water or chloride ions, or will it be reduction of water or copper ions? So you go to your table, you check your table. Okay, when I have a look at oxidizing agents, I can see I have water, I have copper ions. So moving down, copper is a stronger oxidizing agent than water. Copper ion is a stronger oxidizing agent than water. Therefore, copper ion will be the one that is reduced. And then having a look at the chloride ions and water, you can see that water is a stronger reducing agent than chloride ions. So naturally, it would have been expected that water will be the one that will be oxidized. But due to the phenomenon that is called overvoltage, it is not the water that is oxidized, it is the chloride ions. You just need to know that it is because of overvoltage. You don't need to know what overvoltage is. So then it means chloride ions will be oxidized to chlorine, and then copper ions will be reduced to copper. Now, the overall cell reaction, it will be chloride ions, copper ions forming chlorine and copper. Now, in this case, you are also expected to know the observation. The copper that is formed due to the reduction of copper ions will be deposited around the negative electrode. And the chlorine, remember chlorine is a gas. So, since chlorine gas is formed, therefore, and it is formed at the positive electrode, therefore, the bubbles will be formed, will be seen around the positive electrode. So when you are asked to give an observation, you say something that you can see. Something that you observe is something that you can see. So you cannot say an observation in the negative electrode is that copper ions have been reduced to copper. You cannot see the reduction of copper ions, but you can see that copper is deposited on the negative electrode. You cannot say that in the positive electrode, what you observe is that chloride ions are oxidized. You cannot see that, but you can see that chlorine is formed by seeing the bubbles. Chlorine is, remember, you cannot see with your eyes that this is a gas, chlorine gas, but you'll see that a gas is formed by the bubbles that you'll see around the positive electrode. By the way, can you see that in the negative electrode, reduction occurred, but in the positive electrode, oxidation occurred? Remember, in the galvanic cell, in the negative electrode, oxidation occurred, but in an electrolytic cell, in the positive electrode, oxidation occurs. That's why I'm saying to you, you cannot describe oxidation in terms of polarity. But still, when you see that where oxidation occurs, we call that an anode. And where reduction occurs, we call that a cathode. So you define cathode and anode in terms of oxidation and reduction, respectively. Now let us move on to the next electrolytic cell, the chloralkali industry. Remember, it is the electrolysis of concentrated sodium chloride solution. So since it is also a solution, it means either chloride ions or water can be oxidized, or sodium ions or water can be reduced. So you go back to your table, you check. Sodium ions and water. Water is a stronger oxidizing agent than sodium ions. Therefore, water will be reduced. And then when you have a look at chloride ions and water, you can see water is a stronger reducing agent than chloride ions. But due to over voltage, it is the chloride ions that are oxidized. So what happens there? Chloride ions will be oxidized, therefore we call that the anode, and water will be reduced, and we call that the cathode. And you write your overall cell reaction. And here you might be asked, for example, name the gases that are formed. So you must know that it is chlorine and hydrogen. Or you might be asked to write the formula of them, which is Cl2 and hydrogen and H2. Any of those kinds of questions can be asked. Another electrolytic cell, it is where you use active electrodes. So when you say active electrodes, it's, in other words, what we're saying is it is the electrodes that are reacting. And if the electrodes are reacting, the solution, the concentration of the solution will remain constant. So in that case, this example is electroplating. What happens here? You want to electroplate a metal with nickel. So the one that you want to electroplate, it means nickel must be formed around that metal. Therefore, it means nickel ions must undergo reduction there so that nickel can be formed around this metal electrode. And then the one that you electroplate with, we want to electroplate with nickel. Therefore, it means nickel must undergo oxidation. You can also check that using your table. You will see that, nickel ions are stronger oxidizing agents than water. Therefore, nickel ions will undergo reduction. And then you will see that nickel is a stronger reducing agent than water. Therefore, nickel will be oxidized. Therefore, your half reactions will be nickel will be oxidized at the anode, which is the positive electrode, and nickel ions will be reduced at the cathode, which is your negative ions. And the rate at which nickel is oxidized to nickel ions equals exactly as the rate at which nickel ions are reduced to nickel. Since these rates are equal, therefore the concentration of the nickel ions in your solution will remain constant. Why? Because as the nickel is oxidized to nickel ions are reduced to nickel on the cathode. So as the nickel is oxidized to nickel ions at the anode, nickel ions are oxidized to nickel at the cathode. So the rate of oxidation equals the rate of reduction. Therefore, the concentration of your electrolyte will remain constant. Therefore, the overall reaction will be nickel plus nickel ions forming nickel ions plus nickel. Another example of electrolysis using active electrode is purification of copper. So since you want to purify copper, it means copper has impurities. So for copper to get rid of its impurities, it means copper must be oxidized. So it means you must connect the impure copper to the positive electrode so that it can be oxidized. Therefore, impure copper must be your anode. And then pure copper will be your cathode. So then it means impure copper will undergo oxidation and get rid of its impurities, and then copper ions will now undergo reduction at the cathode where pure copper will now be formed. You can also use your table there showing that copper ion is a stronger oxidizing agent than water. Therefore, copper ions will be reduced, and also copper is a stronger reducing agent than water. Therefore, copper will be oxidized. Therefore, your half reactions, oxidation there at the cathode will occur, and then reduction at the anode will occur. The rate at which copper is oxidized to copper ions equals exactly as the rate at which copper ions are reduced to copper. Therefore, it means the concentration of the electrolyte will remain constant. Therefore, your final half reaction is Cu plus Cu2 plus forming Cu2 plus plus Cu. And then the last electrolytic cell that was expected to know, it is the extraction of aluminium from molten aluminium oxide. So in this case, aluminium oxide is heated to form aluminium ions and oxides, or oxygen ions. Aluminium ions and oxides, or oxygen ions. And you must also remember why cryolite is used. Now, what happens then as aluminium oxide is heated? Aluminium ions and oxides are formed, or oxygen ions are formed. Now, aluminium ions will undergo reduction at the cathode. By the way, your cathode and your anode are carbon rods. So carbon rods are inert. They do not take part in the reaction. So the reaction will be of your electrolyte. Now, aluminium ions will undergo reduction to form aluminium. And as aluminium is formed, it is drained there at the bottom. And then oxygen ions will be oxidized at the anode to form oxygen gas. Now, the overall cell reaction will be oxide or oxygen ions plus aluminium ions will form oxygen plus aluminium. Remember that aluminium is drained there at the bottom. That is why we say it is extraction of aluminium. But now, there are certain questions that you might be asked. For example, why do we constantly have to replace the anodes? Remember, at the anode, what happens? It is the oxidation of oxides to oxygen. And this oxygen that is formed can react with these anodes. Remember, the anodes are made of carbon. So the oxygen that is formed can react with that carbon to form carbon dioxide. So after a while, the anode has to be replaced because these anodes, which are carbon rods, react with the oxygen that is formed there to form carbon dioxide. You might be asked to explain the environmental effects. For example, the carbon dioxide that is formed there can contribute to the greenhouse gases. Since there must be heating of aluminum oxide, heating, for example, we know in South Africa, we use electricity, and electricity comes from the burning of coal. The burning of coal also contributes to the greenhouse effect. Why do we use cryolite? Aluminum has high, the temperatures there that will be used are too high. So we use cryolite so that we lower the boiling point or the melting point. Remember, it's molten. You lower the melting point of aluminum oxide so that we don't use much electricity. Now, since we are now done with what I wanted us to do, I just want us to recap on what we did the previous time, just for a little bit. Let us just recap on what we did for the previous time. And what we did in the previous time is the collision theory. I just want you to remember that for the collision theory to occur, two conditions must be met. And those conditions are particles must have sufficient kinetic energy. So you will always have particles, reacting particles. But those that will react will only be those that have sufficient kinetic energy. So those that in the shaded area. And the second condition, they must have correct orientation. What does that mean? It means if, for example, these two reactants, for them to react, they must collide in this orientation. It means if they collide in other orientation, no reaction must occur. And another one, remember factors that affect rate. Surface area. When you say increase surface area, remember you are talking about something that was a big, now it is cut into smaller particles, or it is now ground into a powder. Why? Here, for example, you have a potato. Why do you cut potatoes into smaller pieces? So that you can see when it is one potato, only a small surface area of water covers it. But when it cut into smaller pieces, water surfaces can cover all those potato pieces. Therefore, we have increased what? The surface area of the potato. Therefore, it means now more particles will have sufficient kinetic energy and more effective collisions will occur per unit time. Remember, the per unit time is important because if you give a reaction long enough, there will be more effective collision. But what is long enough? Can be 10 years. If it occurs in 10 years, can we say the rate of the reaction is high? No. So it is important to say per unit time to show that it occurs in a certain period of time. Here, for example, when you increase the concentration, you can see that the concentration, when you increase low concentration, you have less particles in a particular volume. More concentration, more particles in a particular volume. And if you have more particles, therefore, there will be, you can see the dotted line shows more particles in that particular volume. Therefore, when you have a look at the area on the right hand side of the activation energy, you will see that there will be more particles with sufficient kinetic energy. Therefore, there will be more effective collisions for unit time. The increase in concentration, you can just imagine, like, for example, you are in your class. There's 10 of you in the class. You walk around, you will collide. But if in the same class, there's 100 of you, in other words, you have increased the particles in that particular same volume, same class. Therefore, there will be more effective collisions per unit time. And then the last one is the one of temperature. You can see that at T1, you had lower temperature. So it means you had less particles with sufficient kinetic energy. But at T2, which is the dotted line, you now have more particles with sufficient kinetic energy. Therefore, we'll have more effective collisions per unit time. Now, thank you very much for that. And I want to wish you all the best with your examination. Ensure that you prepare thoroughly and ensure that you answer all your questions. Like, for example, I said to you with negative marking, before you move on to the next question, just check that you have answered all the questions in that particular sub-question. Because if now there's negative marking there and you only gave us the explanation without answering the question, it means you'll get nothing, because you cannot explain something without giving an answer. So ensure that you answer all your questions. Just read through your question paper, relax, and give it your all. Give it your best. So ensure that you do all that you can. So good luck with everything, and until we meet again next time, meaning next year in Bloemfontein, when you have to collect your level 7s. Thank you very much and goodbye.